Space by, what was it, Scientific American in 2003. And of course, Spaceship One is on the cover of Time magazine right now as 2004's most fabulous innovation. So thank you for coming. He's going to give a presentation, and then we'll have some questions. You can eat your lunch, and it's going to be a good time.
Okay, well, let me continue. The biggie I felt, though, was not just the generic risks of ground launching a rocket, but the flight control issues for reentry. An X-15 can't do the kind of reentry trajectory that Spaceship One does. The Space Shuttle does a very, very shallow entry into the atmosphere and spends a half an hour decelerating. Never goes over 2 Gs, but it very carefully lifts upward, and to keep from going beyond Florida, it does some zigzag turns, and it does a very anemic trajectory that requires reasonable precision throughout the entire reentry, and is in jeopardy to immediate death if it has a flight control problem. For example, if it lifts downward, it picks up way too much fuel and breaks up. The X-15 is the same thing. An X-15, to fly to 100 kilometers, had to go out about 300 statute miles away and boost to a 40-degree gamma flight path angle, and then it does this parabola and re-enters at 40 degrees, and a good re-entry attitude or angle of attack is 40 degrees. So the X-15 pilot, all he had to do for re-entry is either follow his instruments, or if they're out, just level the fuselage. And he had to hold side slip very carefully because it would couple. So he does a 40-degree re-entry angle of attack. Now, as it's a very high wing loading vehicle, and when he gets to his maximum Gs, his Q is as high as 1,600 pounds per square foot. Okay, keep that in mind. 1,600 PSF. That's a pretty heavy Q. To keep from over-G'ing, he then, as he gets into the dense atmosphere, he just softens the angle of attack. Essentially pushes out of this 40-degree angle of attack to hold 5 Gs. And another thing he has to remember to do is not bounce. He needs to level off when he would otherwise start climbing. Neil Armstrong once in the X-15 was evaluating a G limiter, an automatic G limiter, that was supposed to make it so that he couldn't pull more than 5 Gs. And in working on this, in this phase between when you first pick up 5 Gs and sometime later out at max Q, he was working on it and he forgot to level off. He picked up only a 2 or 3 degree positive gamma. And instead of making a turn to downwind over Edwards and landing to the south, he rolled up over Mojave and pulled 90 degrees of bank and full aft stick, and nothing happened. And he made just this real gentle turn, and he's wondering for the next minute or two, I wonder where I'm really going to land today. He flew right over the Rose Bowl in Pasadena, and where he could dig in and back into the atmosphere enough to dig in, and very heavy wing loading, of course, and it does its glide down at 300 knots equivalent, knots indicated, and he landed to the north on the lake bed and just made it. So a little imprecision is a big deal. The fatal accident of the X-15 was started by an instrumentation problem that confused the pilot, and he got the airplane sideways, and then he got it into a spin, and he got the nose down and picked up too much Q, and it broke up. So anyway, I'm thinking there's got to be a way. That issue of the safety for reentry initially made me decide to not do an airplane at all. Just to do a capsule that had very high drag and that could enter steeper and it didn't have to be controlled. And you got this just kind of a carefree thing. You gotta get there. You don't have to control it. And in fact, I had these relatively large things we called feathers, and you could ground adjust them. If you've got a group of people that are 80 years old, you might not want them to go over 4 Gs. So you get your crescent wrench out and you adjust the stops on these feathers so that when you get to 4 Gs, they collapse and bend inward. And the deceleration then takes longer, but it limits itself at 4 Gs. And then if you get some kids who want to really gut it out, you can give them an 8G reentry. So, well, that's kind of cool. But looking at what it would really take, we originally didn't want to go into the water. We were going to pick it up on a parachute with a helicopter and bring it back to the site. But looking at what limits we would have working with parachutes, I decided, wait a minute, I'm a guy that's done 36 airplanes in the last 30 years. For God's sakes, I got to do an airplane. So I searched for a way I could have this carefree reentry and a very steep reentry, which requires a very low ballistic coefficient, real high drag, lightweight. If you do that, you start decelerating way up high in the atmosphere, and you get maximum Q at about 110,000 feet, whereas the X-15 will get its maximum Q down around 65,000 feet, which is an enormous difference. I found all kinds of configurations that were good, stable, easily hand-flown gliders, but none of them would trim to a high drag at that same CG position for a low ballistic coefficient reentry. And the first configuration I found that did that gave me very high drag supersonically, and trim to very high angle of attack supersonically, about 65 degrees alpha, and yet would still have a good static margin, good flying qualities as a glider at the same CG. Keep in mind, I outlawed a quadruple fly-by-wire flight control system. You just don't find those on small airliners. You find them when you're flying 300 people, but you don't find them on small commuters, and there's good reason for that. And the Spaceship One configuration that jackknifes into a configuration that we still use the word feather, even though there's no feathers on it, but we feather and defeather. That was merely the first configuration I was able to come up with that would provide the high supersonic drag and the good flying qualities at subsonic. Okay. Let me go through this presentation. Since a lot of you saw it last night, I'm going to bounce through, or saw some of these slides last night. I'm going to bounce through I'm going to go ahead and bounce through to some things that I didn't show last night.
Can you make the presentation available?
Unfortunately not, no. I can't make the DVDs available either because of the Discovery, Discovery Channel agreement they made. How many here did see the Black Sky things on Discovery? Oh, not a large percentage. If you're at all interested in this subject, tonight they're running it again, all 3 hours. So if you don't have a hot date tonight and are interested in what we did at Mojave, there's 3 full hours tonight on Discovery of 2 programs called Black Sky, and they're about our program. They're very good. No wind tunnel testing. You know, a long time ago, when the only thing you could buy for CFD was some little stuff that Lon Crow was writing on his little square Macintosh. By the way, I understand you're still doing that. I used that stuff in those days, and you haven't sent me any upgrades. In about 20 years. What's that? Yeah, I'm interested if you're still doing that. In those days, we would either do some low-speed wind tunnel testing, or we would not do any at all and go out and modify the flight test airplane when we needed to tweak it to make it do in detail what we wanted it to do. And we did, in the early days, we did a lot of, what I'm talking about now is back in the 70s when I was doing the whole builds. We did a lot of tweaking of the airplane in manned flight tests, where it was easy to change the airplane's configuration. Nowadays, though, and this has been true for a long time at my shop, we do very little wind tunnel testing. The only wind tunnel testing I did on this entire program was in an area that I got a surprise, and that was resulted to an early tail stall. At FCG, the tail on an outboard horizontal tail airplane is loaded, relatively heavy, and it didn't perform to the CO max that we expected it to, and we had the most danger in our entire manned space program in that we had a nose rise and it locked in at about 20 to 25 degrees angle of attack. It wouldn't come down. Actually, if we put it in feather, to come right down. But Mike tried something else and got it out of the deep stall, or moderate deep stall, before he feathered. That was probably the biggest danger in the program. The fact that our CFD hadn't adequately predicted that, we went out very quickly and did full-scale wind tunnel tests, and we got data in about 4 or 5 days. Now, to do that, we ended up building the whole tail section of the vehicle plus a segment of the wing so that we'd have the upwash in it and put it out in front of a truck and drove it at speed down the taxiway. Because our Reynolds number is what it is at 50,000 feet, we were actually able to do full-scale Reynolds number testing very quickly without scheduling somebody's wind tunnel. Other than that, though, there's no wind tunnel test at all on this program, even though the other 36 airplanes that I've developed in 30 years have all been subsonic. And I looked around and realized that the supersonic airplanes have all been done by government-supported prime aerospace manufacturers. So we are the first little small shop to do a supersonic airplane. And to put an exclamation point on it, we have supersonic almost straight up, which is kind of cool. Let me just move on. Oh, another thing, the ground rules. No stability augmentation system. I wanted to see if we could do this with a hand-flown airplane. And SpaceShip 1 has some deficiencies that we can easily fix in SpaceShip 2 by configuration. It has excessive dihedral effect that has given us fits throughout the program to the point where you have to kind of train the pilots to use their feet instead of lateral stick to fly it. We had to do that because I had to put the spar either on top of the rocket motor or on the bottom, and the feather works better on the top. We've gone to putting the spar on the bottom. The SpaceShip 2s will be low-wing airplanes, longer boom tails. The configuration still works beautifully for feather, but we have the right amount of dihedral effect, and that's a biggie. We also lose directional stability at the highest Mach numbers, and we didn't know it until the first X-Prize flight, but we lost it significantly at low angle of attack. And that's what caused the side slip that coupled to roll in this rolling departure that you saw on. In fact, I'll show it on the DVD. Okay, why would you fold an airplane in half right before you pull 5 jigs? I think I've gone over that, but again, we get very high drag at around 63 alpha is a trim angle of attack supersonic. It trims to almost 70 alpha subsonic. It is just a 2-position configuration. We tested it extensively subsonic during glide tests. In space, you never have to put the feather up while you're aerodynamic. We do that when we're 0 Gs. But it goes up just fine in a glide flight. We've made re-entries at all kinds of attitudes, including a re-entry from 200,000 feet upside down. And let me point out, the pilot, first of all, there is no autopilot in the airplane. There is no electronic device hooked to the flight controls anywhere. You have stick and rudder, and we have trim, electric trim 3 axes, which we need for high Q supersonic flight. Usually you think of needing electric trim for supersonic, you know, like Chuck Yeager had to trim his tail because you don't have any control power supersonic. But actually, Spaceship One's a little bit different. We only need the electric trim to control the airplane for about 40 seconds, and it's not the highest Mach number. When we get above about Mach 2.2, and keep in mind we're going to 3.3, now you can fly the airplane just fine with a stick and rudders. And the reason is the Q is so low. On Brian's flight, the last X Prize flight, at burnout, we're at Mach 3.3, and the equivalent airspeed was 20 knots. So I don't care where your center of pressure is, if you only got 20 knots, you can move your flight control surfaces just fine. I spent enough time on that. This was the biggie, is that we had to build our own motor. The configuration that lets us take the entire propulsion system, all of it, and skirt mount it here in 2 places. You keep in mind, half the weight's forward, half the weight is back. So the skirt loads on mounting this tank are tiny. They're something like 60 or 70 pounds per inch. Essentially, we have no weight penalty for attachment of the entire propulsion system, and the motor is cantilevered. That gives us only one leak path between the tank and the motors. So we've got dual O-rings with a pressure check between, and there's only one place that the entire propulsion system can leak. It has just one valve which goes open or closed, and it operates at room temperature. And I'll tell you, you don't even need to go to Stanford to be able to design a good valve to do that. So this is a no-brainer propulsion system. And the beauty of it is I don't need the highest ISP. We operate it at about 0.52 on Spaceship One in terms of the mass of propellant as a fraction of the total mass at ignition. We'll operate at about 0.57 or 0.58 for the commercial space tourism deal, because we want to be able to fly a couple hundred miles, we want to be able to go to 140 kilometers. But instead of increasing performance by going out and giving up a lot of reliability and paying a lot of money for a higher efficiency rocket engine, for suborbital space tourism, you say, well, gee, this is a no-brainer. Let's make the propellant mass 60% instead of 58%. And that makes an enormous difference. And it costs you nothing, really, essentially nothing, just a little more fuel.
What is your ISP?
About 255 at our flight altitudes. At sea level, all our rocket tests done on the ground it's less than 210, but it's about 255. We do almost all the burning with a very well expanded nozzle. If you see this nozzle here is only a 10-to-1. It's an exit about this big around, a 4.5-inch throat. The nozzle that we fly to space, it's not shown on here, but later on you see the ship, and the nozzle's about this big around. It's about a 26-to-1 area ratio. Well, there's the 26-to-1 area ratio. But anyway, our big job, of course, is to build a couple of composite parts. They're pretty challenging. It's interesting that the environment that this motor sees for thermal protection is much more severe than the environment that your leading edges see coming back from orbit. We have 6,000 degrees for about a minute and a half, and we have pressures running from 600 psi down to about 400 or 450 at the end of liquid. So this is a very harsh environment, And that CTN is what we call, it's a unitized part of the case-stroke nozzle. It's the most difficult composite part we've ever built in scale composites. So we built about 20 of them.
So you said it was an ablative nozzle last night. How
Yes.
do you replace the nozzle, or do you replace the entire system?
We replaced the entire CTN, and details, I'll tell you what, let me get through this and I'll get to that. It's cheaper to replace the entire CTN, and it's safer because you have less leak paths. And we found a way to have the ablative nozzle cost. First of all, I did a very detailed study on, first of all, there is no such thing as a reusable nozzle. There's a reusable nozzle you can run maybe 20 or 50 flights, okay? But there's no such thing as a nozzle that you can run without having to do a lot of inspection and pressure tests and whatever in between flights. That in mind, I found out that the ablative throwaway nozzle is cheaper than the reusable one in operations where you're flying a lot and can build it in a production cell. And then I found out a way that the ablative nozzle costs nothing. So that's why we're going with the ablative nozzle. And the reason it costs nothing is I asked Dennis Tito, who's spent a lot of money to go over and fly in space, I says, you know, what do you got to show for that? He said, I got a video. Well, you know, you take a nozzle that has its throat about like this, the big deal. If you saw it into, with a water knife, saw it into about 9 pieces, you have a beautiful section of this real black burn stuff, and it's really impressive, you know. And you put it on a mahogany plaque. That you were the 2039th astronaut, and here's, you got a piece of your spaceship. See, and what you do is you take the cost of the nozzle and divide it by 9 and sell it to him. So you have, if he doesn't buy it, you can sell it on eBay. So you have, nozzles cost nothing. And again, a lot of things about space travel cost nothing that people don't realize about. I mean, Paul Allen got 40% of his total investment for a manned spacecraft, for a manned space program. He got that all back with one check for the X Prize. And people don't realize he got another 10% just by painting Virgin on the side of the ship. So before even the license fees comes in, he got half his money back. And his program is very profitable just with Virgin. And we've got 4 or 5 others. This is all non-exclusive, 4 or 5 others applying for license to use these technologies. So, okay, there may be simulator guys in here. We did a fixed base, very good simulator. We have a monitor at each window. The 4 front windows look at a screen. And we have sound, we have some vibration, we have full complement of all the switches, and it's a good pilot training device, and it's a good, it is our tool for going in. I mean, we went straight to the sim after that X Prize flight on a Wednesday, where we had the departure, and saying, oh my God, what are we going to do? We got, you know, we're planning on flying on Monday, but we only have 2 weeks to fly. We loaded in, reduced the data from that departure and looked at the frequencies and realized what our directional stability is. We loaded that in, the pilots got in the sim, and right away they could duplicate the departure. And right away they found that if they just didn't pull the trajectory hard at first, where they have to later, when you get to high Mach, push a little bit to get it to re-enter where we promised FAA we might re-enter. Actually, on the flight before that in June, we re-entered over Palmdale, which, you know, these guys don't have a lot of sense of humor. The thing could re-enter over Bakersfield and still get home. It's not a big deal. We got 60 miles of glide range after you put the feather down. But anyway, we found that, first of all, we didn't think that the departure was dangerous. It occurred at only 105 knots indicated, VE actually. And by the time it rolled a couple of times, the damping is very low when you're up there at Mach 2.6 is where it first departed. Mike had to leave the motor running during that because at least another 5 or 6 seconds to make sure we got to 100 kilometers. So he's a little distracted by it, but it's interesting that you know, you look at the video, and this was So not real time on CNN and Yahoo and everything, but so this whole world was watching this airplane do 29 rolls. Okay, which is a record, by the way, for vertical rolls. I believe it's, the space shuttle does like a half a roll on takeoff, but those guys are chickens. But this first roll was a classic side slip departure, coupled because of very high dihedral effect, coupled to roll. And yeah, we got pretty good rates going. It's about 190 degrees per second. Going out of the atmosphere essentially involved only the first 3 or 4 rolls. After that Q is so low, you're not really aerodynamic anymore. And Mike was able to, just with aerodynamic controls, slow that 190 down to 140 degrees per second. Interesting thing was, it was absolutely straight up. If you look at the video shot out the side, and you'll see some of that video later, you see the horizon going by like crazy, and it's all in one place. So you're going straight up. Now when you roll an airplane, and you have all this coupling going on, it's kind of a harsh ride, because you have side slip doing this, and you have all this. When you don't have any Q, and your head is real close to the rotational axis of the airplane, and the motion is just roll, things aren't quite the same. First of all, you don't see anything, because all the way down to here, which you have to turn your head to see the horizon, is totally black. And if that black is wobbling, you don't notice it, because it's just black. Okay? So he had his head real close to the axis of rotation. We didn't have any Q going on for the vast majority of these 29 rolls. And he didn't see anything turning except his display. Okay? So, he hung in there. We have a little predictor that tells us, if you shut down the rocket motor now, how high will you go? And 100 kilometers is kind of something you like to see there before you shut it down. So he let that happen, and he wasn't in a hurry. The reaction control thrusters for space attitude control are set up in the position on the ship for its inertial characteristics with the feathers up, because we felt we should put the feather up right away, so you have time to work on it if it doesn't go up. So that means the inclination of that principal axis is down, so that's where we put the yaw thrusters, and we line the roll thrusters and everything. So you'd have good, pure 3-axis, non-coupled thruster operation. So he didn't have to. I mean, he could have used a roll thruster just fine without the feather up, but he elected to go ahead and wait till the feather was up. And we don't start putting the feather up until your equivalent airspeed is less than 5 knots, which is nothing, and it takes about 15 seconds for the feather to get up. And after it was up, then he just went ahead and moved his stick over. And the reaction controls is on the stick and pedals. If you've enabled it with a switch, there's redundant left and A and B systems. You put the stick over to near full roll, and you're on a micro switch, which opens the thruster. So he did that and got everything damped out by the time he got to apogee. So, and you'll see that. I'm going to show the video later on. Anyway, I'm spending way too much time here, so I'm not going to go into details in the sim. There's our heroes. Kind of neat pictures of some of the fun. I like that picture on the left. That's the White Knight contrail veering off. You have this kind of feeling you want to get out of the way. As it turns out, we can't do an anemic acceleration for suborbital space tourism with a simple vehicle. You could if you had a complex vehicle that had thrust vector control and all the redundancies with that. You could burn the motor longer. But keep in mind, you don't want to be burning the motor when you're near weightless, because you only have 4 minutes of weightless, and you don't want to distract from any of that weightless time. But we have to get the motor shut off about halfway up. And the reason is, if we go farther, Q is so low we can't have anything to control the attitude of the vehicle, because we're using just aerodynamic controls to control the attitude of the vehicle. We're not using any thrust vector control. So anyway, you really can't run into them. This is kind of an optical illusion of it being behind, but it goes with almost 3 Gs forward when you throw the switch. And then it ends up to a little more than 3 Gs at one stage later when you're lighter. But the pilot has a task of pulling about 3.5 Gs, plus or minus a half, for the first few seconds, because he needs to make a good portion of his pull subsonic. It's only 9 or 10 seconds, but he needs to make a good portion of the pull there. If he waits till later, he doesn't have enough control power to make the turn supersonic. This was our bad day. Actually, this is the day when we went supersonic for the first time, but we combined that with Brian Binney, who's a Navy pilot who made a hard landing, and we broke the attachment for the left landing gear, and we're all dirty, and that's how we went off to Christmas. But actually, it was relatively easy to fix. There's no major damage there. There was no even scrapes on the pressure vessels, because we have the nose gear skid protected it. 17 flights. We flew the rocket, the spaceship, 17 times. Now that doesn't mean that we tested and matured its systems only 17 times, because all of its systems, except for the rocket motor, are on the White Knight. So we flew the White Knight 67 times, and we did some flights as long as 4 hours. So we did a lot of systems maturity on the White Knight, and of course a lot of practice and so on the White Knight. In this are 6 flights where we lit the rocket motor in flight. Okay, one where we burned the motor in a cold flow up there 10G, but 11 was the first time that we lit the match and got a lot of thrust. So we did 6 flights with the rocket motor running. 3 of them went above 100 kilometers. And this actual program results was perfectly matched to our most optimistic plan when we started the program back in 2001. Usually that doesn't happen. Usually you write a plan that's success-based, and then you find out, well, we got to fly 15 flights instead of 6. You know, this ended up being our most aggressive envelope expansion that we thought was a credible thing to do, and that's how the program worked. So, from the standpoint of the technologies all working and not having any big delays, not having any reasons to have to refly stuff, our program was near perfect. And it needed to be, because we'd have been out of money. Here's our basic problems that we ran into, and I think other slides ahead show them. Tail stall, outboard horizontal tails. When you have a flight at the neutral point, which, you know, you can fly conventional airplanes at the neutral point, and the tail usually has good margins on the stall. But an outboard horizontal tail, if you fly back to the neutral point, the tail's going to be stalled long before the wing, and that's a big issue. So generally what we do is we fly with very large static margins. However, we had to qualify the case where we got launched and the motor didn't light for some reason. Now, we've got 3,200 pounds of liquid nitrous oxide here and 600 pounds of fuel here. The CG of that combination is pretty good. It doesn't move the CG much while it burns. But if you don't get the match started and you want to dump the nitrous because you want to get rid of half your weight for landing, you can't dump the fuel. So we have to keep 600 pounds here and dump the nitrous here. And doing that, it gives us back to this situation we call pre-emergency FCG. It's not an unstable condition. It's very controllable. It has plenty of static margin yet, but what it does, it puts us in jeopardy at moderate or high angle of attack of having tail stall. And so we built very quickly, didn't even paint it, a full-scale version of the ship, turned it up on the side, put a load cell for lift on the horizontal tail, and we tested all kinds of configurations. and we ended up, maybe it's shown here, no it's not, we ended up with a vortex generator up in front, a fence, and a tip extension. And we qualified that at full-scale Reynolds number. Again, high dihedral effect. This was a problem that made the ship difficult to fly throughout the entire program. The pilots tended to get used to it. Yeah, you need to carefully fly it with rudder, not just feet on the floor and fly it with a stick. And again, we have a good fix for that. We've already qualified it at all Mach numbers on SpaceShip 2. Essentially was solved with pilot training, flying techniques. We were going to put a ventral on the bottom, maybe even a folding one. We were going to go out to the wingtips and put forward swept, high anhedral little wings. These things were minor fixes. They didn't go anywhere near of getting the dihedral effect that we wanted, and we elected to not bother with them. Because as we flew through the program, opened the envelope, we found out, yeah, it's not optimum, but it'll be good enough. Okay. Now, had we done those sort of things, we likely wouldn't have had the departure that we had. You know. But keep in mind, this was a research program. We're not developing a ship. There's no intention to develop a ship that goes right into space tourism. You know, Boeing doesn't build an airplane until when they first fly it. They're almost done with certification, and they make almost no changes to send it out and fly passengers. This was a research airplane. It was not intended to be a space tourism asset. It was intended to look at what the costs are likely to be, and can we solve the big safety issues. So we had no need to make certifiable flying qualities. The low directional stability really caught us by surprise. We had, based on our prediction and our CFD, we expected, and this again is high Mach. This is only like 2.6 to 3.1 Mach number. We had this in the simulator, and we had a lot of flight test data here, and it looked okay. And then on the departure, we had a point way down here, essentially at 0. And we refared that. In fact, some of the data was showing that it may turn that way. Put it in the sim, went out and flew it, and sure enough, we have very low directional stability at low angle of attack. And we solved it by flying a different alpha schedule on the trajectory. And that's the reason that if you watch the flight that we did on Wednesday, and then we flew another one the next Monday for the X Prize, there were absolutely no changes made to the ship. One of them departed from control flight, did 29 rolls. The other one flew perfectly, ran the engine clear down to 22 knots of equivalent, went 13,000 feet above the X-15 record, and it just looked absolutely optimal and smooth. You know, Brian says that's because I'm a lot better pilot than mine. All we did was change the alpha schedule on the pull-up. You meet some neat guys when you do this sort of thing. There's Paul Allen and Richard Branson. They're very different kind of folk. But I'll tell you what, both of these guys were needed to reach the goals that we wanted to do. And what I'm talking about goals is so that everybody, if they want to fly in space, they can at least do suborbital flights. People will know that in just a few years. Even though if you read the Virgin Galactic website, it says this is going to cost $200,000. You get out here 5 or 6 years and you'll know that you'll be able to afford to do suborbital space flying if you want it. Okay. Kids, and this is more important, about 15 years from now, kids will know that if they want to go to orbit in their lifetime, they can. Whereas for all of the past, kids have dreamed about going to orbit. Okay? And for the last 25 years, that dream has softened. If you saw what happened in the 60s, my God, I'm going to go to Mars, right? I'm young enough, I can go to Mars. But what happened after the early 70s, we had Skylab, and we've gone to the moon, we did all these neat things, and everything went downhill. We lost capability, things got more expensive to fly, things got more dangerous to fly. And so there's still kids today that say, man, I dream, I want to be an astronaut. Well, you know, if you look at what's happened in the last 25 years, you can tell them, hey, you're smoking it, kid. You know, go try another day job or something. But my dream and my hope from what I'm doing here is I think we'll show up about 15 years from now, and that will be, kids will know if they want to go to orbit, they can. And there's a possibility of how this activity is going to go. We have very flat activity. Well, first of all, while things are government, nothing happens. Everybody knows that. From the internet or GPS or whatever. It's when we work with things that things take off and do these innovation cycles. We're going to be out here getting bored with suborbital, not only the hard timers and so on doing it, because this is going to start getting affordable for orbital space flight. And before I die, which is out in here, so I want to be able to afford to go to the moon. Okay, let's go ahead and let's see how we're doing. Oh, we're doing fine. Let's go ahead and run these two flights. They're only about 10-12 minute DVDs, and it'll give you a real sense. Those of you guys that haven't watched the videos, this is neat stuff to look at. And we can get the lights down as much as possible. Backlight, and this, bring the sound up on them too, Ken. And these are kind of summaries of we make up a little video summary of each one of the Spaceship One flights. We have cameras all over the place. We've got cameras inside the cockpit looking at the pilot. We have a camera here on the tail of the spaceship looking at itself. By the way, that one is interesting because it shows the operation of the feather. It shows the plume of the rocket motor. We TM that to mission control, and we can see that in real time during the flight. Go ahead and just mash feature and run it. This is not the video I showed last night. These are the two X-Prize flights.
Get over the concrete.
Those are afterburning engines. They're afterburning engines only because they were the cheapest engines I could find.
90.
They're from a T-38. And rocket guys like a lot of noise anyway.
Watch it.
Some of these shots are in a white night, some are in the spaceship. It does look identical. The windows, the cabin, everything is identical.
Gear handle.
The white night cabin could go to space. It's totally identical.
I can see it moving. Starship wind 29010, quick takeoff.
In fact, the actuator retracting that here is the same actuator that feathers the
Space House, Cat 1-2 requesting a clearance to land and your current surface wind.
Not very often, you're up near 50,000 feet, you call the tower and ask clearance to land. And he says, Roger, clear to land. Now, we don't want other people landing during that 15 minutes, because if we have them stuck with a gear up in the middle of the runway, then it's not good. Okay. Almost 3 Gs forward. The sound you hear here is the actual sound recorded in the cabin of the spaceship. Gotta love that, huh? Woo! He had a very good trajectory here. He didn't expect this departure. He didn't have the rolls that he had gotten before on the flight back in June. He was ahead of his gamma schedule.
Okay. Okay, coming up 40 seconds, a little left. Great.
You can see the nozzle expanding now. The thrust goes way down when all the liquid's gone from the tank, but we still burn after. Okay, this chugging. Okay, actually, you have the departure there too. That chugging is when the motor goes in and out of liquid and gas. it's sloshing and it's hammered for about 5 or 6 seconds. Okay. Now, okay, right there he shut the motor down. Now, you can kind of get the sense here, this is really just kind of a space tumble. Okay. He is using rudder and aileron against, and he was able to get rid of about 1/3 of the rate before he got out of the atmosphere. Now, see where the horizon is there? You know, it's very, very close to straight up. The feather has no electricals in it at all. He's moving a valve, which is putting pressure on the pneumatic cylinder. Redundant left, right. Now look at the top. You can see a roll thruster firing off the top of the wing. See, he's got full left aileron there. That's just firing the roll thruster to get rid of the rays.
Shows 334, Mike.
334 was our INS. Actually, the radar showed we went to 337,000 feet.
Okay.
3,000 foot difference was our INS got a little confused with the
Okay, I understand we show Throttle work.
Kind of a neat view.
Heading up to 328.
And right there we knew we had a good X-Prize flight.
The radar constant.
100 kilometers.
Mike, your trajectory looks great. You're going to go just right down the red line to the entry point. He's currently 5.4 east, coming through 334, just about at apogee. Call apogee mark.
This other banner here in the background is noise inside mission control, not like
Yeah,
Mike.
just right in between the go, Mike.
He only hears
looks
from
good.
the captain.
Radar altitude was 338.
This hose, and the reason we have to wear an oxygen mask is the moisture you breathe out, we want to really absorb it, not let it go onto the
Great
window.
job you did.
Window fogging was the only ECS issue that I had to fight on the whole program. We're at sea level cabin, and you don't have the pressure changing like you do in an airliner. It stays exactly that for the whole flight. It's the most comfortable environment.
Yeah, we think all of this is the right way to go on that. The other great flip right.
Changes with power and all that other stuff that they put you through with an airliner. Okay, he's taking some pictures now. The only pictures we had before this flight were stills from video, so they're all low resolution. So we decided to get some pictures. One of these pictures ended up on the cover of Aviation Week. There's nothing to do, and he's not really responsible for an accurate re-entry attitude.
Clear, thanks, and that's it. Everything's cool in the back.
This is later now. We're getting, I think, maybe not yet, just a hint of Q, and you can watch in these pictures a little damp sinusoid of it aligning itself. It's initially with the nose down about 30 degrees, but after you get to maximum Q, you're falling at about a 30-degree attitude or angle, because we do have lift. Okay, now you can see the damp sinusoid. The ship is straightening itself out. There are no flight controls active at all. This is doing it all by itself. That's very high Mach air, but it's still very low Q. Okay, he's pre-breathing. In other words, you breathe hard and then you can handle the G's better. He's intentionally breathing hard. Watch his oxygen mask. Watch it pull off of his face time. There he pushes it back up. Where supersonic is very smooth when at max Q at 5.5 Gs. But when you see the tails really start to shake and his head starting to shake, that is all subsonic. Because we get the big buffeting when we're subsonic. It's a picture taken from the ground. He's turning back towards the airport. You can turn. You can use rudder or ailerons to point the nose, but you can't change angle of attack or side slip. You can change it, but only by a couple degrees. Okay, now we're subsonic and shaking. And he's putting the feather down.
Got the important side. Copy that, you're found on glider.
those boxes behind him where the seats are were just filled with all kinds of memorabilia. All my employees got to fly something in space. And we flew a bunch of weird stuff on You'll hear about it later.
I can 7 miles.
Okay, now we got just a light glider, very low wing loading, stall speed of about 80. And oh, he didn't get enough rolls, so he did a roll. So he wanted to do 30 rolls in the flight, I guess. Now, actually, that was on the flight card. We do that just so a pilot doesn't get accused of doing something outrageous. It's called a roll evaluation. If he wants to do it, he's fine to do it. Everybody approves, yeah, you want to do an aileron roll, you've already been approved. And again, nice version picture. The landing gear is gravity and a spring. We just release it, and springs get it going good, and then inertial's down. The nose is a skid. It's hard maple block. We grind off about 3/4 inches of hard maple to stop the airplane, and it's lighter than using brake. The wheel brakes are off the long easy, and they're primarily just for steering at low speed. We don't use them for taking everything. Come on, let's go with the other DVD, or maybe just let it touch down here. Okay, let's put the other one on. Now, notice on that, Mike says, "Yeehaw," when he says that, when he knows that nothing's bad's going to happen that day. He's got his gear down. He really is. Oh, one thing we don't have on Spaceship One that you must have on a space tourism is you need a throttle for the final approach. You need to have speed brakes so you can go shorter or longer. We decided not to do that because we felt we could do a good job at setting up the pattern, whatever. Hold off just a second. Spaceship has an LRD of more than 7 for glide, and it's about 4.6 when the gear is down. We have these big forward-facing doors. So that's the only throttle you have. You can also put the rudders clear out. Like a long easy, each pedal is hooked to a rudder, so you can increase it a little bit. But we don't have a big effective throttle for final approach. But anyway, when Mike does his yeehaw, it tends to be when he's you got the gear down, he's lined up on final, and it's clear that he is going to touch about 1/4 to 1/3 of the way down the runway, and you know, everything else is easy. Mike's a very, very good pilot. He's not going to make a bad landing. Now, notice on this one when Brian Binney says yeehaw. Now, keep in mind he had flown the airplane 3 or 4 times, the Spaceship. The last time he flew it, first of all, this is in October. The last time he flew it was in December the year before, and he flew the first private supersonic flight, but he made a hard landing and damaged the airplane quite a bit. Now, there was a flight control deficiency which distracted him for that hard landing. We had put a viscous damper in the flight controls to get to lower the risk of having a buzz of the elevons at transonic speed. It was a flutter issue. It's a buzz issue, and those dampers got real cold. And what they didn't give us more viscous damping because we had a very good low temperature fluid. But what they did is they gave us a high breakout force. And so we had added a device to the flight controls for the first time that gave a pretty high breakout force. And that makes things a lot harder to fly. And that distracted him when he started the round out. And he felt that there was some kind of a stall problem, and so he didn't complete the flare. And that's why he landed hard. But anyway, we had solved that by putting some insulation, some heaters on the dampers after that. Brian had not flown it from December until the second expert. Okay, go ahead, Brian.
Okay, since yesterday.
This gives you a little sense of our mission briefing. This is the crew chief of the SpaceShip, Steve Losey.
We installed the JJ cam, serviced all the bottles, including the nitrogen bottle.
Well, it's interesting, we had no squawks on the ship the last 3 flights. We came back with no squawks. All the space flights returned with no squawks on the airplane. That was kind of neat. It's pretty unusual, actually, but it's kind of neat. Brian's a Navy combat pilot, flew in first Gulf War, and he flew an American flag. This is Corey Burt, the project engineer of the White Knight. We're pumping some air into the J-85s to get them started. This is taken from the low altitude chase plane, taxiing by. We put some extra insulator around the body for the taxi only, because we wanted to more accurately control the temperature of the nitrous. Because to get more performance, we operate the nitrous at very low voltage. This is a view out the side of the spaceship window. If you
Make sure he's squawking.
Copy that. Are you squawking, Brian? That's good.
50. 60. 70. 80.
This is not an aerolio strut. We have a lot of leakage problems because of cold soak on Proteus. That's actually a rubber damper on the main landing gear. This turned out to be a very good idea. There's absolutely no maintenance for the whole program. In our Proteus, we have about every other flight to these cold temperatures where we have maintenance struts.
And it's up in the video. And oxygen.
A lot of times, simplicity is a lot more important than performance. That's kind of a good lesson learned if you're going to go out and fly things for people to afford them.
You're a little quick. I think you're on 135. You can check with Brian. Next stop, 25.
At 25,000 feet, we level out both ships,
Yep.
and we do a very careful, with everything off, a very careful cabin leak check.
Copy that.
And we usually get about 5 to 10 foot per minute. I mean, the cabins are essentially hermetically sealed, dual seals. So this is taken from the tail of the White Knight. The other camera that you saw was taken inside the tail of the station.
No.
Negative, sir. Yeah, we got 2 good lines, and we're heading up there.
We're an afterburner now. We don't use afterburner for takeoff. We use it just for the last 15,000 foot climb.
Oh, you're doing great.
White Knight Ranger, flight Branson, flight level 370.
White Knight through 37370.
And like, that would be like, I'm looking at 134 knots, 41,500 pneumatic, going 21 miles from the release point. Camera is on. Gonna do trim checks.
Verify that you've annotated the recorders.
Okay, this is my night flight 17P pilot duty for October 2004. Time is 14:38, 14:15, 16, 17 PayPal.
Shuttle approach. White Knight starting to turn in. We've got a 180 trying to make it slow. Okay, White Knight's coming to 1 minute here. Scout status.
Forgot to go for release ignition. How about to go? 3, 2, 1. Release.
Release. Fire.
There's 2 switches. Bam. Go.
Good point. Good point. Coming 10 seconds, Brett. Brakes look good and low. Okay, drop the nose down. Looking great at 20 seconds. Is that okay?
Good, all right. Little lateral inflation down.
Copy that. 30 seconds. A little nose up. Tempo probably okay now. Feeling great.
Well,
Okay, 40 seconds. The energy's on the line. The trajectory looks good.
copy.
him from going to low or negative alpha. All we did was give him a bottom limit of pitch trim.
Go right. 300,000.
That meant if you shut down the motor now, you go to 300,000 feet. Right there. So now we have a prediction that we just won $10 million.
Roger, shut down.
Notice how slowly he went up to shut down the motor. I told him, I said, I want you to get the X-15 record too. So he just went and wandered up there. Came out of the atmosphere, very low range.
Okay.
By the way, that's where the shuttle landed.
84 seconds. 84 seconds, the shutdown is clean, the feather is green.
He ran the motor 84 seconds. The automatic timer was set at 88. So we ran it almost the whole burn.
RCMC on.
Copy that, Brian. It's moving and it's green. The CTM's a little warm, but looking fine. RCSA looks nominal.
I need to operate something where there's no hinge moments at all.
Okay, we do show the feather
No
all the way.
gravity. When you operate on the ground, you got gravity. In the flight, you have gravity, but here we're weightless. It's just zero. Right there, we just knew we won $10 million. That was that is if he gets down alive. You still got to get down alive.
You're going to want to orient.
That's Paul Allen behind me, by the way.
Hey, Doug, copy that northwest.
That's great. Feel good?
I'm feeling great.
That was on that we covered. It's also on our Christmas card this year. In fact, our Christmas card is one of these kind of child ones that you pull down and the spaceship comes up. The spaceship was printed on paper that was flown on space on this flight. So everybody that gets a Christmas card has something that's been to space.
Okay, pointed position is coming down to 350, and current position is 5 southwest, correction, 5 south of the bullseye. Looks like the entry point is between main base and north base.
So what he's saying there is we're
I can
reacting
keep up
over
with that for
Edwards
GPS,
Airport.
that's good, and again, orient north or west.
We're about maybe 10 miles south of where we had aimed. Keep in mind, this is not a precision. Oh, there he's pulling the camera behind you. This is not a precision trajectory at all. It doesn't need to be. Oh, he's doing some flight tests now.
Right, yeah, that would be good.
Brian actually lined it up very well for re-entry, so he had very little oscillation coming in.
I'm doing great, Doug. Camera's stowed again.
I don't know why it is, but test pods don't talk a lot. You know, you like them to say a lot of things, and they just
And
kind of
it's
stay with it.
northwest. You want further heading, right?
Affirmative. I would expect back high key.
Now you can hear that very high speed but very low Q molecules hitting the ship. And you can see a
Good
very,
green here, Brian. Don't worry about temps in the back.
very long period of damn sinusoidal.
Hey, here comes the Jeeps.
Yeah, that is a ping pong on a straight.
There's 3.
3 gauge.
5 Jeeps.
5 gauge. We're going to lay the space tourists almost flat. We take their seats after boost and lay them down. Open up the bars, let them float their bodies around, and then they end up back in the seats, and we're going to be almost flat for the re-entry.
And roll right if you can, that'd be good.
Okay. What he really means is yaw to the right. You
Either 70,000
can't roll it,
feather at your discretion.
but you can do it with the aileron control.
Feels a little loosey-goosey right now.
Copy that.
Maybe subsonic now and buffeting.
You're going to want to get the roll pin back to neutral as your defender. Later on, we'll do 63 now, 63 now.
Okay, feel good about the feather?
Yeah, we do here. when you can.
Or CS is off.
You're going to want to start a right turn to the north as soon as you're covered.
It's really not necessary to turn the RCS off. It has almost no effect when you're flying in the atmosphere. There's a little lock that comes up and pulls the wing down. Now, these are the propulsion guys. For some reason, they always applaud the feather coming down.
Okay, copy that.
Maybe go ahead and roll out to the north of binding down over to E-check and do Hamlet quality as well.
But just the air noise gliding sounds a little bit like the rocket motor near the end of its burn.
We're about done from this end, Brian, with green for landing.
Roger, copy that. Just see the extra down below. I'll be circling in this area.
Good luck to that. We got you all in place. Brian, not to mess with you there, but when you reboot it, just verify that your altimeter is somewhere close to 3005.
Good call.
Okay, stand by the gear.
Roger, 130 here comes the gear.
Looks good. Looks good. Got 3 green?
Now we're L over D of about 4.7.
Got 12 in there, pretty good. Looking good. Right down the middle.
That's a gear door that shakes in the buffeting of the front gear door.
It looks great. There you go, there's 200.
That's 200 feet being called by the chase.
100 looking good. There's 20. 5, let's level up. 4. Keep it coming down, looking good. 4, 3, 2, 1, and 1 foot. 1 foot. Sweet there. Congratulations, Brent. Thanks. Super lit. Good job, Brian. Yeah.
That's the E-copy.
Okay, I think what we'll do here is I've bannered about a lot of the things we want to talk about. Let's go ahead and open it up for questions. We've got quite a bit of time. Yes, sir.
What's the future of Spaceship One, and when do you and Paul get together?
We're still arguing about what to do with Spaceship One. Paul is inclined to say, listen, this 50 years from now will be looked at as a historic artifact, a historic airplane, because it opened up the private use of space. And he wants to put it right in the Air and Space Museum. I want to keep it available should we need to do some testing to support Spaceship Two development. There is other things that we looked at during the program after it was announced that we could do with it. We have 5 different organizations, 3 of them government, that want to use Spaceship One to fly science payloads. Okay. 2 NASA centers actually and NASA headquarters. And DARPA, there was an article in Aviation Week that DARPA plans to fly some payloads on Spaceship One. There is, not surprisingly, people have figured out that, gee, maybe there's a military use for something that can kind of loiter around and then all of a sudden fly real quick up to 150 kilometers and land in another country, and very quickly take a picture instead of waiting for a satellite to come around. But I tell you the one thing I have decided, that we're not going to use Spaceship One for any science stuff. And the last thing that I told NASA, who's been bugging the daylights out of me, well, first of all, they want access to the program. They want to know what we're doing, and I believe that that's not a good thing for them to know anything. Well, if you read Lost in Space by Greg Clerks, you'll find out why. But they found out about my program the same time you did, when it was unveiled in April of 2003. the last thing I said to NASA headquarters about science use of it, I said, you know, you guys have a space station and you have a space shuttle. And the very fact that it's almost impossible for students who build a little satellite to fly it on the shuttle. I said, that's not my problem, it's yours. You've got excess payload, you've got a space station up there doing almost no science, and I'm not gonna help you with that, because I'm gonna be busy on flying people as soon as I can. Okay? You ought to solve that problem for yourself, because you've got a lot more capability to do science in space than I do with my little suborbital ship. And you really need to solve the problem that you yourself created. And that maybe after we've flown at least 10,000 people to space, I might get interested in doing some science, but I'm not interested at all right now. Now, there's another point I wanted to make here, and I've lost it. That's what happens when you get 60 years old.
Another question.
Maybe another question we would like to.
Maybe aggressive question.
It was really a good thing I wanted to tell you too.
Come back.
Go ahead.
Well, maybe it was about the military, I don't know how to use this, but my question is regarding the $50 million prize for orbital flight. Any plan on going after that?
Well, tell you what, I'm kind of where I was in the year 1997 or 98 on Orbital. I think I've got one of the solutions to about 3 of the problems. But I'm not ready to go out and spend somebody's money building a vehicle that takes people to orbit, because I want to solve, at least in my mind, that I have a good chance of solving these other problems. First of all, I don't have a solution right now that I'm comfortable with that we can have safe enough operation taking people to orbit. But I think it's coming. I've got one of the solutions for a very big part of the safety issues for orbital space tourism, but I'm not ready yet. I'm continuing to work on that. And we will be doing some work related to orbital access over the next handful of years. But I'm not starting a program with a confident design in place to solve the problems of us going to orbit yet. Now, will I? I certainly hope so. But lacking the ideas, and keep in mind, these ideas are probably more likely to come from you guys than they are from me, because you guys are not real busy. You have more time to think about solutions, unless you're trying to get good grades on all this liberal sludge they teach us.
Another question?
I expect to do it on the schedule that I showed you, though. And I certainly hope that we'll have good solutions so we can be confident that we can get the affordability where it belongs and get the cost, get the safety where it needs to be. Any mature transportation system, that when I say mature, I'm talking about as cheap as it can be, because it's had decades of competition where the guys that sell cheaper tickets get all the market share, and then somebody fights for that, and it levels out. And you know, a motorcycle, a car, an airliner, an oil tanker, you name it, bus, these things are mature transportation systems. They cost, their direct operating costs about 3 to 4 times the fuel cost. Okay. If you apply that to space access, which I think you can, and when it's truly mature, suborbital flight will cost about $700, and going to orbit will cost about $16,000 or $17,000. Now, of course, we're not going to see anywhere near that for a long, long time, but that's where it has to flatten out.
You said you had a handle on problems? What was the other two?
I'm not. I'll tell you. Here's another thing too. We won't do that in public. It's too difficult to do, and that's the reason that I want to attract you guys to think about coming to work for us as a career. We don't do this and debate it and get help from others out in the open, because the help ends up slowing your program rather than helping it. We put Spaceship One out for others to see only when I had to go outside for flight test. And I expect that unless I have a customer that vehemently disagrees with me and I can't talk him out of it, Branson seems to be that kind of a guy. I don't know if we'll do Orbital with him, but unless we have that, I will do an Orbital program in secrecy also, because there's some big advantages in doing that. The biggest advantage is if you don't tell anybody your schedule, you never have to tell them why you're late. I didn't tell my customer the schedule. I didn't meet the schedule. I was late. I did it with the amount of money that I told him it would take, but I did take longer. And it's good not to be under schedule pressure when you're doing research, because that totally destroys your ability to make the right decisions. Yes?
Along with the comment you just made, I think about half of us would probably drop out of school tomorrow and come work for you.
I have talked someone who was near the top of his class into quitting school and coming to work for me without a degree. He was at Cal Poly, and he had finished his engineering and his science. All he had was this other sludge they teach you. And I said, listen, I don't need you to know that. Quit right now and come to work. And he did. And he's the guy that developed the simulator in the avionics for the ship. I did promise him that if he really wanted to get a degree, he could go back later and do it, but I needed him to work right away. And he did. About 4 years later, he went back and finished those units and got a degree. But it's, I won't look at your grades.
Good. I like building stuff. I don't like studying.
What I'll look at is your hobbies, and what you do with your spare time, to see whether you have passion for the thing that you're going to be doing. And people who have passion for that, they generally do that when they're not on the job. And you know, the fire in someone's eyes is so much more important than the grades in his transcript. So I don't. We do have a little bit of requirements for those with advanced degrees. I have 2 people at my shop that I flat need that, and they end up doing. The beauty of it is they end up doing that kind of work that needs that kind of knowledge and that kind of experience, and they do a lot of it. Unfortunately, a lot of people go out and they'll go all the way through, get a PhD, and they'll go out into the industry, and if they're working on anything that's fun, you know, I consider things that are fun or things that you're developing that are new, that go out and change the world. In general, they don't use that knowledge a whole lot. So I don't like to say, gee, I'm going to bring in this guy because he's got a PhD, and then I can't offer an environment where he gets to use that knowledge very much. And I don't think that's right. I have had so much better experience getting brand new kids right out of college with the right attitude and the right work ethic than getting someone who's worked for Boeing or Lockheed, because those people usually will poison the process. If you get somebody from NASA, he will think that it's good, and he should be rewarded and paid more because he designed something more complex than it needs to be. And he prides himself in that. Well, we don't do that. We reward somebody who comes up with an idea that makes it simpler and more reliable, not necessarily more complex. Another thing that's different in my shop that you cannot find at the primes because of the labor union laws is that you will not be asked to design something unless you're capable of building it with your own hands. You don't design something that's made on a machine lathe unless you can go out in the shop and run the machine lathe and make the part. You don't design a composite rib unless you're capable of going out there and putting on the gloves and doing the layups and doing the bagging and making the part. Now that simple little rule, all of a sudden, just like that, gives you respect from the engineer and the shop people. Because the shop people will not respect an engineer who is incompetent in the shop. And you don't have that esprit de corps there, and it doesn't work. Another thing too is if you design something the shop hasn't built before, in other words, even if it's a nuanced difference, if there's something different than the shop is used to building, you do go out and build it in the shop, not just have to be able to, you do. So an engineer who designs something that's different, he goes out there and he builds it with the shop people. Now the neat thing about it, or the reason that you have to do that, is sometimes a guy will try something that won't work. It's not manufacturable. And that's fine. I applaud him for trying, because if he doesn't try things that may not work, there is no way we'll have a breakthrough. You understand? If we take something, if you design only things that we know will work in the shop, there's no way that you can be involved in improvements on design. So when you go out there and fail a lot, you are the one that is putting us in the best position to find something new. Only if you're failing. Now, so here's the thing: if you go out and it doesn't work, you're the designer. You're the guy that made the drawing and the procedure, and it's not working. See, you suffer yourself personally. And what that means is at 4:30, when the shop guy is over there clocking out, you don't want to suffer at 7 o'clock in the morning. So you'll stick around, go back up to your computer, and you'll change it right now, because you don't want to be embarrassed that you designed something that doesn't work in the shop. See the way that kind of works there? All of a sudden, just by having that basic rule, I get probably 7 or 8 times the efficiency of developing new things than the primes do. We have some processes that are just unbelievable to the primes. I can take a CATIA loft, and we approve a loft. We say, yeah, that's what we want to build. And within 24 hours, be laying up the part in a tool. And usually that takes months working in the primes. We have a phenomenon. We just upgraded it recently. 50-foot 5-axis, very high speed 5-axis CAD or CAM machine that we bought from Italy. And so we're doing a lot of upgrades. We're moving into a much bigger building. 2 projects I've got coming up cannot be built in my present facility of 4 buildings. So we're in a big growth time now. Well, a lot of our work is going to be, not all of it, a lot of our work is going to be space tourism. And I hope to carry that all the way to about low Earth orbit just as soon as we possibly can. And I need people who work with their hands, who design stuff, who don't mind going in and trying new stuff, and have the courage to try something new. Because if it don't work, you don't get chastised for it at our shop. You get appreciated because you had the courage to try something new, and that's the thing that's missing. NASA right now, based on the rules that they put in after the Columbia accident, they cannot ever do, unless they change the rules, they can never do flight research anymore. They can't even fly the current ship back to the Hubble telescope. They can't take risks. They can't do something they're not absolutely certain will work. What that means is the next thing they develop, if they're allowed to develop it, is going to be worse than the thing they're flying now. It's going to be more expensive. And the 2 accidents have added at least 10,000 people to the the program, each accident, everything goes downhill, goes worse. Last time I checked, the Hubble telescope is relatively close compared to Mars. And if they think they're going to get our tax money to go to Mars, they better tell us that they have the courage to go to the Hubble, I think. Yes?
How many people are in your company? How big is it?
140. We typically have between 4 and 8 projects going on in the shop. And typically from 20 to 40% of our work is the kind of stuff you never ever see. You don't end up being in magazines. That's all I can say about it. But we do our toughest problem in hiring is getting people who either have security clearances or can get them quickly. You know, they don't have everything from drugs to a relative from the wrong country or whatever, or a criminal record such that they can't work on classified programs.
You'll find a lot of those at Lockheed and
So,
Boeing.
yeah, but we can't use the Lockheed and Boeing people. No, I have hired a tonload of people from Lockheed and Boeing, and we can't, in general, we can't keep them. There's an occasional exception.
It might come.
But most of the people that we hire out of the primes don't end up staying.
Counter reception is with regard to the security clearance of somebody that is international citizen.
Real tough. If you don't have a U.S. citizenship, I can't hire you at all. I can't let you have access to our intranet. So you really can't work as a normal employee at scaled. And we did that from a guy from a country that's reasonably friendly, England. and I had a lot of trouble keeping as a career staff guy from England. So, you know, I don't do just the commercial stuff. So in general, I have to have U.S. citizens, and I have to, I don't have to. I can hire people that can't get a security clearance for whatever reason. But my flexibility in using you is lower. Keep in mind, people will be I'm the project engineer of the SpaceShip that's been out of school for about 3 years. 3 or 4 years. That's a pretty neat job. Okay. So youngsters right out of school do neat stuff real quick at my shop. And I need more project engineers. It isn't something that just goes to the seniority of the guy that's been there 20 years. That's not the way it works. In fact, one of my best project engineers came to my shop with a toolbox. And he doesn't have a degree, but he's a very creative designer. And he, on his own, went out and learned the things that he needs to run structural analysis. And he is smarter than the rest of the guys on tooling methods and visualizing load paths and laying out structure that can be built. In fact, he has this cover of Sport Aviation this week, that beautiful little yellow airplane with the world-class workmanship. That guy is one of my top project engineers, and he does not have a degree.
Is it the low drag plane?
Yeah. Yeah. It's very nicely done for drag, too. He seems to be smarter than that without a college education than most people. Yes?
I realize that you're really busy and there's a lot of liberal sludge out there, but would you ever consider teaching?
When I left Cal Poly, I said, I'm going to come back here and teach when I retire. And I do enjoy classroom teaching. I mean, what I'm doing here for a couple hours is a lot of fun. I mean, really is. I don't see myself retiring soon. I thought I might. I had worked a lot on my golf game, and when you have this kind of you know, you get on the cover of Time magazine on on 60 Minutes and whatever, you pick up some bennies that you don't normally have. I've been invited to play in the Bob Hope Chrysler Classic Golf Tournament, along with the pros, and along with Bill Murray and Joe Pesci and Rush Limbaugh and all those guys that play as a celebrity. So that's kind of neat, you know. So I thought, well, you know, I would have thought that I'd be doing a lot of that and not working as hard after this program, because I really didn't think much would happen after Spaceship One. I kind of looked at it as the model of the Voyager deal. We went out and did something real hard to do. It attracted a lot of people's attention. Yeah, we got all the covers and TV programs that were on Letterman and Carson and whatever then too. But the thing is, the Voyager program didn't have anything to, there's nothing follows it. What's happened with the space tourism thing, and when I say space tourism, I'm talking about space tourism just for, not just for suborbital, but looking ahead on how we're really going to go to Mars. Not just a few of these Houston folk go, but how we are going to go. And I'm fascinated by that, but it isn't just my fascination. There is so much work out there that you cannot believe it. There are multiple, I've got another meeting on Tuesday with another very credible company that wants to license this technology to build spaceships. And yes, we'll work on things that will be competitive with Richard Branson. We have to do that. And there's so much fun out there that I don't see myself anywhere close to retiring. But I need somebody to take over, and it might be you guys right here at scale.com. Your resume in, and I don't mind if you quit before you get your advanced degree. We need help in rocket propulsion. We need help in aerodynamics. We need help in structures. We need help in avionics. Not necessarily all in that or in that order, but I need help in all of those areas, and I need really help for people who just want to put their hearts in it, not just come to work and run software. Yes, sir.
You're talking a lot about space, but what about developments in the airplanes? Are you still interested in airplanes at all?
Yeah, when we moved up to cars, there was a whole lot less interest in buggy whips. I don't mean to be that. I have lost a little bit of my passion for light airplanes, partially because I lost my medical about 6 years ago. So I've got a wonderful boomerang which I can put 4 of you and me in and go out here and take off and fly nonstop to Hawaii, and I built it to fly around the world and visit neat places. But I don't fly it very much because I have to have another pilot when I fly it. We have done several general aviation research programs lately, you know, the V-Jet and the Visionaire and now the Atom. The Atom likely is the only one of those groups that's really taken the right path towards its development certification, and they'll probably will get it certified next year and be selling them. So that's kind of nice after being very proud of the Starship that we did in the early 80s, and finding out that they only built 50 airplanes, and Beach is trying to buy all of them back now. By the way, the guy that chases our space flights with his Starship, there's no way they're going to get his Starship. Something like a cold dead hand. We did a program, we did 2 programs for Toyota on general aviation. And the older one was by far a better airplane. The airplane that we did for Toyota about 12 or 13 years ago was a phenomenally good general aviation airplane. The one that we did for Toyota more recently is just an average ho-hum kind of an airplane. We designed the first one, and the second one we only built it and flight tested it. We didn't design it. So I don't have a lot of interest to go in and put our best talents on a very modest improvement for general aviation. That's probably the most honest way I could say it. I need to put our best talents, and I need to put, first of all, we have probably 13 programs going on at the scale right now. Most of them are studies, but we have 4 to 8 things all the time being built in the shop. I only put my close attention on 1 or 2 of them at a time. The space program is pretty much gotten all of my attention the last 3 years, just because it's done, and for the first time in a while, as I did a lot of detail design on it. I just, you know, I'm passionate. I don't mind going and designing push rods and little nit noise stuff on it, just because I just want it perfect, you know, and I kind of want to do it myself. Well, I've gotten over that a little bit, and not just gotten over it a little bit. I mean, most programs I won't be involved in hardly at all technically. Usually all of them in the concept stage I am. An example, you know what the X-37 is? Built by Boeing, $200 million. It looks like a X-34 kind of, and it's just going to do glide tests at Edwards. $200 million, and all it's going to do is just glide down to Edwards. They decided they're going to use the White Knight instead of the B-52 to launch it. And I went down and looked at that, and I mean, you just got to shake your head. This thing is so unnecessarily complex and costly that, let's put it this way, we do have a program, an active program. We're going to be launching it. We'll probably fly the first launch on it in February or March. And we've got 40 Boeing people coming in. I've got 2 or 3 people on the program, and 40 customer people. And we're going to be the one that develops the interface, and the hooks, and the pads, and the electricals back and forth. And we're going to launch it so they can do some glide testing. I have so little interest in that program that I had one meeting with my engineers to tell them what I thought they need to look out for on the launch system. And I probably won't pay any attention to the program at all. To me, I'm not, maybe we're helping a little bit because we're not going to charge them very much to launch it like they would if it went into the government organization of Dryden and used the B-52. You know, that they would have so many people working on it and they spend so much money. So maybe we're helping the taxpayer a little bit. But to me, the technical interest in it is zero. And we used to do every little general aviation thing that comes along. I've got a couple of general aviation or commercial aviation things that look fascinating and challenging because they're different and there's some interesting aerodynamics, and we'll do those. But we'll say no to a new program that's just ho-hum. And we just flat don't want to grow so much that we lose our culture. So I doubt if I'm going to be doing anything in general aviation anytime soon. Yes, sir.
What do you see as the primary cause of all this excess complexity of projects that come out of the prime? Is it something cultural embedded in the company, or is it imposed by outside regulations?
You know, that's a real good question, and I hope you guys get out in the industry and help them solve that. Let me just march through and point out the most obvious thing that happened and how ludicrous it is. You know, we did some phenomenal things, starting from pretty much off-the-shelf missiles all the way to a lunar landing capability, and built the most wonderful spaceship that's ever been built, and that's the Grumman lunar lander. And then within a week after the first manned lunar landing in July of '69, we approved the go-ahead of Skylab. And 4 years later, it was manned in space. And I don't know if you've been to the Air and Space Museum in Washington, but you can walk right inside the Skylab that they didn't fly. It's flight hardware. And it has a much bigger diameter than the International Space Station. And my favorite video in space is these guys running around that using centrifugal force to run. You've seen that. And I'm thinking, my gosh, we did that so quick. And it was a neat thing to do, and we did it so quick. Well, there was a decision made to try to solve the problem of why it's so costly to put things into orbit. NASA went out to Congress and it says, I know this is going to be horrible, expensive, and you're going to really cringe, Congress, when we tell you how much it's going to cost, but we've got to spend this money, because if we do, we will lower to 1/10 the cost that it takes to put something in orbit. And therefore, we've got to do it so that in the long term we'll save money. And they sold Congress on the Space Shuttle, which cost 10 times as much to put a pound in an orbit as throwing away a Saturn V. Now, trying to go 1/10 and end up with 10 times, that's a factor of 100. That's a mistake of 100 or 1%, whichever way you look at it. That's a big mistake. That's an enormous mistake. Now, here's the thing though. It's all right to make a mistake, but you ought to recognize it early in the game, and you ought to either quit or at least be honest about it and say you made a mistake and try to recover from it. In this country, long before they flew the Space Shuttle, they should have recognized that it's wrong to have your only access to send people to orbit having to fly a big cargo ship, which in fact the Space Shuttle is a space station, isn't it? Now, every time you send a person to orbit, you launch a space station, and you fly it for a week, and then you have to deorbit it and have 45,000 people spend months to turn it around. It doesn't take a rocket scientist really to realize that that's stupid. And this country should have gone out in the 70s, not the 80s after the shuttle was flying, but in the 70s, and gone out and found a way to make something more reliable and lower cost to put people into orbit than Soyuz, which is the only practical way to go to orbit there is. And why we didn't do that, why NASA, in order to support this big mistake, refused to do anything else, because they didn't want it compared cost-wise to this horrible mistake. The International Space Station is primarily a political justification. It was a way to keep the bad guys from going to the wrong countries, because we got to have the right jobs for these Russians now. And it's a way to get international cooperation. And during the Clinton administration, the requirements on NASA dealing with the International Space Station were all political. NASA was used as a political tool, not a research tool, not a technology tool. And then the shuttle feeds on the station feeds on the shuttle, and they're both justified only because of each other. And then every time one of those programs has a little bit of a cost increase, what does NASA do? It goes over and it eliminates like an aeronautical program, deep space program or something. Can you imagine how neat it will be to explore deep space when it is so cheap to fly that we can put thousands of probes out to the planets instead of just one every couple of years? And we should go along on some of those thousands of them, sure. Next question.
So to do that type of work, we need a little more infrastructure and more developments in the private sector to research.
You need to have the understanding, yes, we can do this. The fact that there's a private deep space probe being developed now. Be launched in about 14 months, I think. By the way, it'll have a little piece of SpaceShip 1 in it to go to Pluto.
You equated science.
And what?
NASA. You equated science missions with NASA. That's sort of stupid.
JPL does pretty good work. I wouldn't close JPL, but I close every.
My point is that there's a lot of non-NASA science missions that are going on. You mentioned hands-on work. Stanford and Cal Poly, through their satellite work, have tripled the number of private university research